Well, good afternoon, everybody. It's a pleasure to be here as part of International Asteroid Day. I wanted to talk a bit about, there's been a lot of speculation recently about whether we could use asteroids for resources to build things in space, or maybe, as Hilary alluded to, even mine things on asteroids that would be very valuable to return to the Earth. So I'm going to talk about that. I'm also going to talk a little bit about lunar resources, because I think if we're going to talk about space resources, then we should be talking about both the moon and asteroids. So I just wanted to say something about the economics of space resources, and they're kind of summarized on this graph, which shows how much energy it takes to get from the surface of the Earth. I assume you can see my pointer. The x-axis here is distance from the center of the Earth. So this is the center of the Earth here, and the Earth's surface is there. And then this is the energy, this massive hill you have to climb in order to get off the Earth to a low Earth orbit, a geostationary orbit, or largely out of the Earth's gravity well to get to the moon. And then I hope you can see the moon here. The moon has its own gravity well, of course, but it's much less deep than the Earth's. So this is the energy you need to get something off the surface of the moon into cislunar space, or Earth-Moon system space. If we wish to do things in space that require us to build things in space, it's going to be a lot cheaper to source those materials or that energy in space itself rather than launching it from the surface of the Earth. Because if you wanted to do something in geostationary orbit, for example, to launch all that material you need from the Earth, you've got to climb this massive hill. Whereas if you mined it from the moon, you've got a little hill to climb, and then it's actually downhill. If you mined it from asteroids, the asteroids are further away, of course, even the nearest ones. So they'd be on this blue line, but several slides to the right. But essentially, if you wanted to mine things on asteroids to use in space, then you've got negligible gravity that you have to lift those materials out of. So this is the primary economic reason for wanting to mine asteroids. So there's a hierarchy of possibilities that you might want to use space resources for, and they're listed in this box. So the first thing you might want to do is to, if we're exploring the moon or Mars or even asteroids, and we need materials to facilitate that exploration, then it's going to be clearly cheaper to source those materials locally than it would be to lift these materials all the way from this massive mountain all the way into space. And this is called in situ resource utilization, the utilization of space resources in situ to facilitate scientific or exploration activities. We could build on that, and this is a second bullet point. If we wish to build really large-scale infrastructures in space, or develop a space economy that would facilitate communications infrastructures in near-Earth space, scientific infrastructures, energy infrastructures, tourism even, all of these activities are going to be much economically more viable if they utilize resources that have been sourced in space rather than lifted from the surface of the Earth. And then finally, as Hilary alluded to at the end of her talk, we might find some things in space that are so valuable that actually it would be economic to go into space and mine those resources in space and then import them directly into the world economy. There aren't many of those things, I think, but nevertheless, I'll talk a little bit about what ideas have been suggested. So I do want to stress the scientific value of using space resources, potentially. Many scientists are quite aghast is the wrong word, but skeptical when it comes to talking about space resources, because it seems very, commercial. There are all these horrible commercial companies and they're just trying to make money, and science is supposed to be purer than that. On the other hand, science does require a lot of expensive stuff. And as we explore the universe, we may wish to build quite a lot of big, expensive stuff in space. So here are some examples. Picture on top right shows the Darwin interferometer. So this was a proposed European Space Agency interferometer to study planets around nearby stars. And it's several space telescopes. All have to be built in space or be cheaper. The point is they'd be cheaper if you had to build these large telescopes in space. We might imagine telescopes on the moon, the Lunar Observatory. We might imagine a lunar outpost, which would be a bit like an Antarctic research station on the moon. It would facilitate a fantastic amount of exploration of the moon, but it's going to be economically much more realistic if many of its resources are sourced on the moon and carted from the Earth. And here's a slide from the film The Martian, with Matt Damon carrying something to his big pressurized vehicle. I mean, in the fullness of time, the exploration of Mars would also benefit greatly from a in situ scientific research infrastructure. Again, a bit like an Antarctic research station, but these things are probably only going to be feasible if we utilize as many in situ space resources as we can. Just to seed a thought in your minds, I mean, there might be even a long-term environmental case for utilizing space resources rather than continuing to mine some of these resources from the surface of the Earth. So the big picture here shows what I think is a bauxite mine. I think it's in Australia. The big digger is encroaching on the forest behind. Now, one of the reasons that mining things on the Earth is detrimental is we're destroying habitats of creatures, animals plants that we share this planet with, but of course they don't benefit from our activities. Our activities are wholly destructive from their point of view. Whereas if we could move some of this activity to places that don't have indigenous life forms of their own, like the moon, so here's a picture of something similar going on the surface of the moon in bottom left, our industrial activities would not impinge so much on the other inhabitants of planet Earth. So this could be a long-term environmental case. So it's not just an economic case. There could be, in the longer term, an environmental case for utilizing space resources rather than terrestrial ones. I mean, put it this way, from an environmental point of view, it has to be preferable, I assume, to strip mine the moon or to strip mine an asteroid than to strip mine the Amazon rainforest. I mean, the difference in harm between those two possibilities seems obvious. But of course, this isn't an option we have at the moment. We don't have a space infrastructure that's able to mine the moon or asteroids yet, and until we develop such an infrastructure, then this isn't an option that we'll ever have in front of us. So it's possibly one reason for developing a space economy, to give us this option in the longer term. Anyway, so asteroid resources first. So previous speakers have already told us a lot about the geography of the solar system. So everyone will be aware that most asteroids occupy the so-called main belt between the orbits of Mars and Jupiter. But from a space resources point of view, it's the near-Earth asteroids that are easier to access. And so at least initially would be the focus of a future space resource industry. There are a lot of them. There are more than 20,000 known near-Earth asteroids, over 100 meters in size. There'll be many millions of smaller ones, currently mostly uncatalogued. But as Marco pointed out, they will become catalogued given our very sophisticated and sensitive telescopes that we now have. Of the near-Earth asteroid population, then we've got, from a resource point of view, I think we'd probably be most interested in the carbonaceous asteroids like Bennu or Ryugu that Hilary and Rami have both mentioned. And these comprise perhaps 10 to 15% of the near-Earth asteroid population. And they're of interest primarily because they're volatile rich. The most volatile rich ones, perhaps 10 or 20% by mass, H2O. And then, as Hilary also mentioned, the metallic asteroids. I mean, these are much rarer in the near-Earth asteroid population. But they're still a few percent of asteroids, so that's still quite a lot of asteroids. And they, as Hilary pointed out, they're mostly pure iron and nickel with some significant cobalt and then some platinum group elements, which may be of interest. And here's a picture that both Hilary and Rami showed of asteroid Bennu currently being visited by the NASA OSIRIS-REx mission. So we're going to learn a lot more about these asteroids from missions like OSIRIS-REx. So Hilary's talked already about the composition of meteorites, and we infer from the spectral types and spectral similarities between asteroids and meteorites that we think we can guess what particular types of meteorites have come from which particular types of asteroids. So here is a hand specimen of an iron meteorite. Hilary showed a similar picture. You can see the crisscrossing pattern. This is the Wittmann-Statten pattern of intergrown camacite and taenite iron nickel crystals that you get in iron meteorites. And so iron asteroids like 16 Psyche are probably similar. And if they are, then they'd be mostly, so in this case, almost 90% iron and 10% nickel and 0.5% cobalt. But then you've got all of these other so-called siderophile elements that chemically partition with iron, ruthenium, rhodium, palladium, etc., iridium, platinum, gold. These are there in sort of tens of parts per million quantities by mass. So they're not, hugely common, but they are about as rich as you can find in a natural resource, because nature has already refined these and concentrated them to go with the iron in the iron nickel asteroid. So Hilary alluded to this in her slide. If you currently present prices, prices of these materials fluctuate, of course, but they're in the range of like tens of thousands of dollars per kilogram for most of these elements, which means that a pretty modest iron asteroid, something much smaller than 16 Psyche, a 200-meter diameter iron asteroid would be worth $100 billion at present prices, just looking at the platinum group metals that it contains. Now, of course, there's a big caveat here, though. This has caused some of the would-be asteroid miners to get very excited because they think they can make a fantastic fortune mining these asteroids. But of course, if you were to suddenly import all these precious metals to the Earth, then the market in them will collapse, or the price will collapse because the supply will have been increased. So it's not obvious if you start mining asteroids that these very useful materials will still be tens of thousands of dollars per kilogram. So the would-be asteroid miners, I hope, have a more sophisticated economic pricing model for this. But actually, I'm a bit skeptical that importing these materials is ever going to be that economic, importing them directly to the Earth. Whereas, of course, for building things in space, it's not so much the platinum group metals that will be of value, but the iron, the nickel, and perhaps the cobalt will be very useful if you're building things in space, regardless of whether you wish also to import the platinum group metals that you may have refined to the Earth. For use in space, I think the carbonaceous asteroids are probably going to be much more valuable, at least in the near term. So picture at top left shows the Natural History Museum's sample of the Avuna carbonaceous meteorite, CI meteorite, but the CIs are the most volatile, rich meteorites, and the I stands for Avuna, so that's like the type specimen of these meteorites. The CM chondrites are similarly, but not quite as volatile. Rich, but these two asteroid meteorite classes, they're very volatile rich, so 10 to 20% water, carbon rich, several percent carbon, and relatively, by the standards of many rocks in space, nitrogen rich, so 0.1 to 0.3% nitrogen. Nitrogen, for reasons I'll come to in a minute, could be quite a useful material in space. Quite a useful element. So if we then consider a 500-meter diameter carbonaceous asteroid like Bennu, and we take the lower limits of these percentage compositions, this is why I've got greater than here, 7 million tons of water, 1.4 million tons of carbon, 70,000 tons of nitrogen contained in such an object. Now, water will obviously be valuable as a space resource. In context of human exploration, of course, people will need water to survive, but water is also easily, provided you've got an energy source, splittable into hydrogen and oxygen. People also need oxygen to breathe. Hydrogen and oxygen in combination is a very useful rocket fuel. So water is would be a very useful substance to have. And bear in mind that if I go back to this slide, bearing in mind that a cubic meter of water weighs a ton, if you want that water and the hydrogen and oxygen it contains to be doing things up here in space, you really don't want to be lifting it up this massive energy well. You really need to source it in space. And the carbonaceous asteroids would be ideal for that. Carbon and nitrogen, I mean, if we're going to be serious about doing things in space on a large scale, then at some point food is going to have to be grown in space. So local sources of carbon and nitrogen would be important, as well as water, in order to do that. And of course, it's all very well to say that we need oxygen to breathe, but actually humans can only breathe oxygen, you know, at a partial pressure of about 0.2 of a bar. So we need a buffer gas to mix with our oxygen in our moon bases and Mars bases, and on the Earth that gas is nitrogen. So in the space environment it might be beneficial if it was nitrogen as well, but this requires an in-space source of nitrogen, and again the carbonaceous asteroids might be a source for that. So I now want to say something a little bit about asteroids on the moon. So a picture on the left shows the moon orbiting the Earth. That was taken by the Galileo spacecraft on its way to Jupiter in the mid-1990s. Picture on the right shows a large lunar far side crater, that's Daedalus crater. But anyway, the point is the moon is covered in craters, so this means the moon has been hit by a lot of asteroids in the past. So potentially, if not all the asteroid material is vaporized on impact, then there may be fragments of asteroids on the moon. If there were, then going to the moon to find fragments of asteroids from a resource point of view might be easier than going to the asteroids to find the asteroids, because the moon is much closer to the Earth. It's uniformly close to the Earth. It doesn't, the distance from the Earth to the moon doesn't change in the way that it does for between the Earth and any given asteroid. So if I'm looking for asteroidal resources on the moon might actually be easier than looking for asteroidal resources in the near Earth, in the region of the near Earth asteroids. So how might we find them? So metallic asteroids, there's already an argument that many of the magnetic anomalies that have been discovered on the moon, this is a lunar magnetic anomaly map, the high colors show the places where lunar magnetic anomalies occur. This is the far side on the left and the near side on the right. This is the South Polar Basin, which is a large impact structure on the far side of the moon near the lunar South Pole. Anyway, so metallic asteroids will leave a magnetic signature, and we might locate them on the moon through flying magnetometers to detect their magnetic fields or signatures. So if we were to visit these localities, we'd find hopefully an iron meteorite, but entrained in it would be the nickel, the cobalt, and the platinum group metals. If we're going to start searching the moon for crashed asteroids, though, we might also, if we're going to be operating on the moon looking for crashed asteroids, we might as well also be looking for the moon's indigenous resources in addition. And the moon has a lot of those. So this image kind of shows the mineralogy of the moon. The near side is on the left, the far side on the right. Basically, the high titanium mare basalts are colored in red. So if you were after iron, titanium, magnesium, silicon, and oxygen, you'd go to the red bits. The yellow areas are the low titanium mare basalts. So this is where you'd go if you're interested in iron, magnesium, silicon, and oxygen. And the blue bits are the anorthositic lunar highland crust, which don't contain iron, magnesium, or titanium, but are very rich in calcium and aluminium, which are also useful materials, especially aluminium, and silicon and oxygen. So the moon has its own mineral resources. The moon has its own volatile resources, and this beautiful picture taken by Japanese Kaguya spacecraft a few years ago, decade ago now, flying over the far side of the moon. Large craters. This is the crater Shackleton here, the lunar South Pole. It's a 20-kilometer diameter impact crater. And the point about craters at the lunar poles is the sun is always on the horizon at the lunar poles, which means the interiors of craters are always dark, they're always cold, perhaps about 40 Kelvin or even less. And in such cold, permanently shadowed regions, water is stable as an ice. And there is now very strong evidence that water ice exists in these polar craters. So this would mean the moon, in addition to whatever crashed carbonaceous asteroids it may retain, the moon will also have its own sources of water in permanent shadowed craters at the lunar poles. The moon, because it's a large, active, planetary-sized, small but planetary-sized body, has its own internal geological processes which have refined other chemical elements. Nature has concentrated through geological processes other possibly useful materials that generally aren't concentrated in asteroids. And the rare earth elements, so that's the group in the periodic table from lanthanum to luteum, plus yttrium, scandium. But anyway, in the rare earth elements in the periodic table, these are they're not all that rare on the Earth, but they are extremely useful because they've got a wide range of catalytic and electrical, magnetic, chemical properties. Everybody's smartphones and computers rely on these rare earth elements. And the moon has had geological processes which have concentrated them. And on the near side of the moon, it's highlighted in this colored area here to the western part of the near side of the moon, sort of around the Imbrium impact basin, so-called prosolarum creek terrain, which nature has concentrated these materials. So if we're going to be operating on the moon looking for raw materials, we could be looking for crashed asteroids. But in addition, we could be looking for materials that the moon has concentrated on its own, like the polar ices and rare earth elements, and maybe well be other minerals. I just want to do a quick comparison now between lunar resources and asteroidal resources. So considering the asteroidal resources first, the image there shows the main belt asteroid Gaspra. So that is a main belt asteroid and quite big, 16 kilometers long, just there to illustrate. But anyway, the advantages of sourcing raw materials from asteroids is their asteroids themselves are small, they therefore have negligible gravities. In terms of energy to get there and back, some of them are easier to access than the lunar surface because their own surface gravities are so low. On the other hand, unlike the moon, they don't stay a constant 380,000 kilometers away. So they can approach the Earth relatively to a few Earth-Moon distances, some of them even closer. But then because they're in independent orbits about the sun, quite eccentric orbits, may be many years before a given asteroid becomes close to the Earth again. So this would, in terms of mining a given asteroid, this would complicate things, that the distance between the Earth and the asteroid is constantly changing. And that's not the case for the moon, obviously. On the other hand, nature has concentrated in the metallic near-Earth asteroids, iron, nickel, the platinum group metals, and nature has concentrated in the carbonaceous near-Earth asteroids, the volatiles, water, carbon, nitrogen. These will be very useful materials. On the other hand, in general, near-Earth asteroids are not concentrated in many other useful elements, like lithophile elements like aluminium, titanium, the rare earth elements. I mean, they have these elements in their cosmic abundances, more or less, but the asteroid bodies have lacked the geological processes to further concentrate these above their background levels. On the other hand, if we turn to the moon is uniformly distant, uniformly close to the Earth. It's always there. It's never going to go anywhere. Lunar geological processes have enhanced the concentrations of many potentially useful materials, so the polar volatiles, aluminium, titanium, rare earth elements, in different places on the moon. But then in addition, the moon's own indigenous resources will be supplemented by crashed asteroids that may therefore be sources of iron, nickel, carbonaceous material, platinum group metals, and so on. But the wider point, and this is the final point I want to make, is that the moon lends itself to the gradual development of a commercial and scientific infrastructure in the way that a given asteroid doesn't. Because the moon is uniformly close to us, it's got a finite, a reasonable, modest gravity of its own. It's got multiple uses, scientific uses, commercial uses, maybe tourism in the perhaps not as far future as we might think. So there are many reasons for wanting to go to the moon, and therefore it lends itself naturally to the development of a surface infrastructure that would facilitate the acquisition of space resources in a way that a given asteroid doesn't, because in a sense, human activities on the surface of the moon would provide a market for many space resources. Okay, thank you very much. I'll finish there, and I'm happy, of course, to answer any questions.